One mission, to glorify God.
Amen.
One goal is excellence through obedience.
Well, that's the mission, yes. Very, very good. Okay. One goal, one mission. Today is Friday. We're going to talk about linear independence. This is really a yes. I killed it. Why else do you think I'm in funeral black? Yeah. Okay. This section is a culmination of a lot of ideas that have been covered in the past sections. If you are still catching up on those lectures, I bid thee please catch up on those lectures so that all these things can come together. An indexed set. Oh, and you have the attendance sheet rolling around, right? Okay, perfect. An indexed set of vectors. And we'll call this, let's have P vectors, so V1 through VP. And then each one of these vectors is going to have n entries, let's say. So Rn is said to be linearly independent. And this is what we're defining here, linearly independent. If the vector equation, and so we had to take x1 times vector v1 plus so on and so forth till we get to p, because we have p vectors in our set. And we'll set this equal to the zero vector, has only the trivial solution. Just as a refresher for our last lecture, what did we call it when we had, we could write a system of equations, write a vector equation and set it equal to zero vector? We had a word for that. What was it? Homogeneous. Yes, homogeneous. So we're saying that these vectors in this set are going to be linearly, we call them linearly independent of each other, so long as when I set up the homogeneous equation, the only solution that you're going to get, the only solution you're going to get is the trivial solution. Okay, does this make sense?
Yes.
The set, and then so let's use the same set. So V1 through VP is said to be linearly dependent. Linearly dependent. If, okay, there's this funny math symbol shorthand. Do you remember what this one means? There exists some scalars C1 through CP. I need P of them. And I'm going to say NR. This indicates that they are scalar values, not vectors. Here's an important qualifier. Not all zero. So I can't have just a list. I can't have P zeros here. I need to have at least one of them non-zero, so not all zero. Such that C1 times V1 and so on and so forth down to CP VP is equal to 0. And if we're actually able to do that, if we're able to take some scalar weights, not all of them have to be 0. Actually, we require that not all of them are 0. And we can get it to equal 0 vector like this. So in other words, a solution. We call this, that equation becomes a linear dependence relation. In other words, it's saying, okay, it's satisfying the definition of being linearly dependent, so then the actual description of how we know for sure that they are linearly dependent is in itself called the linear dependence relation. Okay, that's theory over there. Let's go through an example and see what this is about. Let's V1, let's define this as 1, 2, 3, V2 as 4, 5, 6, and then V3 as 210. So we want to determine if our set of vectors v1, v2, v3 is linearly independent. Is linearly independent. What I'm going to do in this example is show you how you can take a definition from a textbook and actually use that definition to solve problems irrespective of what that problem ends up looking like, okay? So the first thing I'm going to do is ask myself what this math word means. Linearly independent, okay? Well, my vectors, my list of vectors here, my set of vectors is going to be linearly independent if it's going to tell me exactly what needs to be satisfied. This equation needs to have only the trivial solution, okay? So if I'm asked to check or to compute or verify if a set of vectors is linearly independent, your brain should think, okay, well, the only way it can satisfy the definition of being linearly independent is if it satisfies this condition. Ergo, maybe the way I solve this problem should be oriented toward attacking the very condition that makes it definitionally what I want it to be, okay? So if I want it to be having only the trivial solution, let's actually set that up. So x1 times v1 is 1, 2, 3, plus, what would the next one be? Times
2, 4, 5, 6.
And then
V3, x3 times 2, 1, 0.
and what are we setting this equal to? And then how many entries of zeros? 3, yes. 0, 0, 0. Okay. And so what about this equation needs to be true? It has, read it. Okay. So you don't need anyone to tell you to do that. It's a 300 level math class. There's a really awesome thing called critical thinking, where I don't go, here's an airplane, ooh, and feed you with a spoon, okay? You say, wow, I am a grown adult. I have the spoon in my hand, and I also have the direction of where the food is on the plate, so maybe I feed myself, okay? So not all of the problems you're going to solve are going to look like this. Does that matter? No. Okay, you don't forget to eat just because it's now soup instead of pasta, okay? You can figure it out. You know the destination, you know the definition, you can work these things out. So we know how to solve these. I'm going to set up an easiest way to just do an augmented matrix, yeah? So 1, 2, 3, 4, 5, 6, 2, 1, 0. And then we want to augment this with our 0, 0, 0. Because why would we want to actually row reduce this? Well, if we can row reduce it and actually just find what that solution set is, that makes it very, very clear whether it's definitionally linearly independent or not. What happens if I solve this and I end up getting a solution besides the trivial solution? Yeah, it's not satisfying this. What happens if I go through this and the only possible solution is just 0, 0, 0?
Then you're true.
And it's linearly independent, yeah, because it satisfies. It only has the trivial solution. So does the motivation for why we go from this and then now we're setting up this type of problem make sense? It's entirely motivated by just what the definition is, which is why this will be one of the first math classes you might take in your life where actually memorizing written definition becomes as important as knowing how to do just basic procedure, okay? And that's the conceptual gap. That's the next step in your maturity as math students. This is a pretty straightforward one to do. We can practice again. How do I identify the first pivot in the top row? I'm going to go to topmost, leftmost, non-zero. Happens to be this guy right here, this one. And then once I identify that, what am I trying to clear out under? Yeah. All the things underneath it need to be what value?
0.
Yes, excellent.
So if the 4 and the 1 were switched, so would it be still be 1, right?
No, it'll be 4.
No, because if the 4 was here, then the 4 would be the topmost, leftmost, non-zero entry. So irrespective of the value, we just want topmost, leftmost to start the pivots. Okay.
And then when can you like switch rows? Can you do that all the time? Or
You could technically do it whenever you want. If you want to be efficient, I wouldn't do row like switching around unless only do that if you have something like if you have zeros above pivots. Or like if I had zeros here and numbers down here, I would actually want to bump that up top.
What if like I had like a one of, like for example, if we didn't have a one in the first row, but we had a one in the second, is it better to switch the second row to the first row instead?
Oh, so you're asking if like the actual value matters for choosing the pivot?
Yeah.
No. So long as it's not 0, you can make anything work.
No, I think he's asking if the top pivot was like the 4, and then the row below it was a 1. If it would be effective to switch the rows, so that the 1 is at the top.
Yeah, if it will be better. So like.
Oh, so like just
so
make
if
the,
we
yeah.
didn't have a one on the first row, it feels like, let's say a 3, and then in the second row we had, instead of a 2, a 1.
Okay.
Would it be better to like switch rows so that it would be in the first row instead?
If we're talking about, is that easier arithmetic? Probably.
Okay.
If we're talking about if you have to do it that way, no. So it's an optional step. If you want to make your arithmetic easier for yourself, by all means make your problem easier for yourself. However, it is not, you will boil it down to exactly the same solution set at the end of the day if you do all your arithmetic right. Does that make sense?
Okay.
So yes, preferably it's by convenience in this example there happens to be a 1 in our first pivot, so that's going to make it easy to get rid of this. But there was nothing in the algorithm or that says that has to be the value 1 in order for the algorithm to work. Does that make sense?
Yeah.
Okay. So that's a question of ease in actually applying it to a specific problem versus just whether or not it actually has to be a rule. Okay. So here, if I'm going to get rid of this 2, I'm going to take 2R1 and subtract R2. That's going to replace my R2. And then to get rid of the 3, I'm going to take 3 times R1 and subtract the R3 to replace R3. So the top row remains unaffected, 1, 4, 2, 0. The 2 goes away to 0. Double the top row and subtract the second. 8 minus 5 is 3. Double the top row, 4, subtract that, 3, and then zeros. Bottom row, so now I'm using this equation. Triple the top row, subtract. 3 minus 3. Triple, 12 minus 6. Triple, 6 minus 0. And then of course we have 0. Now here, we need to have, we can get rid of. So if you've done enough of these problems, you'll recognize real fast that nothing is going to stop me from scaling all that down to 1. Nothing's going to stop me from scaling that all down to 1. Then I'm going to have duplicate rows, so one of them is entirely unnecessary. Okay, so does it make sense if I kind of skip forward and go 1, 4, 2, 0, and I'm going to say, okay, these are basically equivalent because I can scale that one down to 0, 1, 1, 0. There's nothing stopping me from going 0, 1, 1, 0. 2 exactly of the same row. We only need to keep the top one. 0, 1, 1, 0. And the bottom one gets cleared out.
Wait, so how did you get it cleared out? Like, wouldn't it be like 1, like 0, 1, 1, 0?
Yes. So we could scale this one down, and it would be 0, 1, 1, 0.
No, the third one.
Well, you can just divide everything through by 6.
Yeah, it will be 0, 1, 1, 0.
Yes.
Yeah, but then you subtract so you can get rid of it.
Oh, yeah, yeah.
Yes.
Oh, yeah.
So remember the rule. If you have exactly duplicate rows, the bottom one, just eliminate it. Clear it out to zeros. So I'm just doing that here. Okay. And then now I say, basically in the second row, I have the leftmost in the second row is a 0. So am I allowed to make this a pivot? No. Is that 0?
No.
Okay, so this becomes our next one. Now notice we already kind of cleared this one out. So now when you're in the backward phase, I just want to make sure I clear the one above it out to 0 as well. Okay? So the way I can do that is I can just take R1, whose value in that specific spot is 4, and then subtract 4 times R2 to replace row 1. So then now 1 minus 0 is 1. 4 minus 4 is 0 as desired. 2 minus, and then we need to not forget this thing. So 4 times 1, so we're really doing 2 minus 4. Wait, what? I'm bad at arithmetic, so I had me think for a second. Wait, 2 minus 4
Oh, because
is minus 2. Okay, yes, and then 0.
Minus 10.
Is 0, 1, 1, 0, 0, 0, 0, 0. Okay, so now this is a row reduced echelon form. I know that because our pivots have zeros underneath and above them. Notice we're going to have a free variable. That's okay. Whenever you clear out an entire row, you're going to have a free variable. It's guaranteed. So this tells us, if we literally just interpret this, this is x1 minus 2x3 is 0, and then x2 plus x3 is equal to 0, and then x3 is free. Here's the thing, though.
Can we not just have some -2?
Yeah.
Where?
Wait, is
Like,
it?
yeah, the first row, we can just do like
2R2
But if I...
plus R1.
There's no need to. This is already in the row reduced echelon form.
Because that would put a 2 in the second.
Yeah.
Oh, so yeah, never mind.
Here's the thing, though. What was the original question?
Is it linearly independent?
Okay, so again, in order for it to be linearly independent, by definition, what's the condition?
Only the trivial solution.
Okay, everybody read.
As only the trivial solution.
Okay, ergo, let's come over to our solution set. Can we escape the trivial solution here with a free variable? Yeah. So you tell me, definitionally, what are these vectors?
Linearly dependent.
Why are they linearly dependent?
Because they have
Specifically, the homogeneous equation has more than just the trivial solution. Do not make me read this definition again, okay? If we're able to get solutions that are not the trivial solution, then does this condition get satisfied?
Yeah.
So if I'm able to make a solution that is not the 0 vector, does this condition get satisfied?
No.
And if it doesn't satisfy the condition, what do we say about the thing that it's supposed to be defining?
It's not.
No can do. And so it's linearly dependent.
We say no.
Okay? So that is one of many, an infinite number of types of linear independence problems you can solve. In general, it's going to boil down to, can you identify an augmented matrix, reduce it, figure out the solution set, and then just ask yourself the question. Does it check out? Does it not check out? Okay? If we want to, if say a problem asked for, like, give an example of one such linear dependence relation. So one of these guys. In other words, can I write out the weights that adjust the vectors so that it tunes it to 0? Yeah, I can do that. The way I need to do that, since x3 is free, I really can just choose kind of whatever I want for x3, yeah? So say I make x3 equal to 1. So say I say, let's let the free variable be equal to 1. And then what happens? So then I plug that into here. I would get x2 is equal to -1. Because that's the only way I can get back to 0. -1 plus what we're setting as 1 gives me 0. And then x1 minus 2, so then x1 is equal to 2. So these become the weights for these vectors respectively that forms a linear dependence relation. So I could say that my one such, there are infinitely many because I didn't have to choose x3 equals 1. I could have chosen x3 equals the square root of pi for all it matters, right? So the linear dependence relation, or one such linear dependence relation, is if I take the x1, so I'll make a line here. So the x1 value of 2 multiplied by v1 minus 1, because it's x2, so minus 1 times v2, and then x3 was 1, so plus v3. This is one possible linear dependence relation. So if you are asked, show that a set of vectors is linearly dependent by giving one possible linear dependence relation, that's all it's articulating. Okay? Is it saying, describe the solution set and then pick one of your infinitely many solutions and then make those the weights of your linear dependence relation. Okay, so does this thing make sense? The relationship between identifying whether it's independent or dependent, and then transitioning into a dependence relation.
I'm confused. How did you do that again?
What is V1?
V1 is going to be the constant of that.
Okay, V1 is defined for you by the problem.
Oh, okay.
Okay, what is V2?
Defined.
Defined by the problem. What's V3? And did we not spend time setting up this exact equation?
Yeah.
Because that is satisfying by definition what we're looking for here.
Yeah.
Okay. And then once we did that, we figured out the solution set, chose one such solution, and then just decided to express that in a dependence relation.
Oh,
Yes. So I'm using V1, V2, and V3 as shorthand, so I don't have to rewrite V1, V2, V3, and the numbers. Yes. If you wanted to put 1, 2, 3 instead of V1 here, that's fine. If you wanted to put 4, 5, 6 here, that's fine. But this is also acceptable, especially if it's been defined for you in the problem. Okay. So why do we have this linear independence stuff? Well, it's because you'll notice that if we're dealing with column vectors, and the immediate application that we kind of drew was, well, hey, if I can take columns of something and that's a column vector, then I can start expressing matrices as basically a matrix with a bunch of vectors in it, and those vectors are the columns. So we can ask a very, very equivalent questions that will be helpful for solving some of these. So suppose A is some matrix is equal to, and then it's going to have these column vectors A1 through AN. So I have n columns. Then the homogeneous equation, homogeneous just means put the matrix equation equal to 0, vector, can be written as x1 a1 plus so on and so forth until xn an is equal to 0. And by golly, doesn't that look familiar to what we just had exactly on that spot on the whiteboard? Slightly different symbols, doesn't matter. It's the same ideas. A constant multiplied by a vector in a linear combination set equal to 0. So immediately, our brain's thinking, a definition of linear independence just had exact bearance onto this situation. And just because I'm now thinking about columns instead of an arbitrary set of vectors that have the same number of entries apiece, it's exactly the same thing. So all of the conclusions are going to follow the same. So if there is only the trivial solution, so we're given this condition, so we're saying there's only the trivial solution, then what do we know to be true by definition about these vectors a1 through an?
They're literally independent.
Independent, yes. Because there is only the trivial solution to the homogeneous equation. Then we just happen to call a1 through an, they just happen to be conveniently the columns that we stripped out of the matrix. So then we can call those the column vectors. Then the column vectors a1 through an satisfy the definition of linearly independent. Why is that such a big deal? Well, because then now when you're solving, if you want to know about linear independence and you're given a system of equations, just expressing it in a matrix by itself, you can start thinking about each one of those columns as a vector, and then their relationship to itself is going to be linearly independent if you end up having only a trivial solution. It's all going to be exactly the same. If there are non-trivial solutions, what can we conclude about our column vectors?
Linearly dependent.
then our column vectors are, again, by definition, linearly what? Convince me that you're paying attention, please. Linearly what?
Dependent.
Okay. So, another way we could express this using mathematical notation is we could say if we have only x is equal to 0 vector for a solution, then that's going to imply that we have our set of vectors a1 through an linearly. Which one is it going to be if we have only x equals 0? Independent. And have your thumb on your notes to be able to flip back to when you wrote the definition of linear independence. Because I know that we just covered the definition, so have it at quick reference so you can look back at those properties. And then if there exists non-trivial solutions, that's going to imply that my set of column vectors is what? Existence of non-trivial solutions means what? Dependent. Okay. So far so good. This is essentially a restatement of the definition. It's just given now through the context of a matrix A and its column vectors. Out of curiosity, how many of you have been following along reading the textbook with the sections? So that means 90% of the class is 2 weeks behind? Readings through 1.7 are due on Sunday night, midnight, okay? You gotta keep on top of that in this class. We're going to determine if the columns of this matrix A is equal to 0, 1, 5, 1, 2, 8, and 4, minus 1, 0 are linearly independent. Okay, so if I'm asking if they're linearly independent, what is an equivalent perspective? What's the equivalent question that's being asked here? Yeah, basically, if I make this now a homogeneous equation, when I get that solution set, I better only have the trivial solution. Otherwise, what do I say?
It's dependent.
Dependent, good. Okay, so do you see what I did there? I took the exercise, and then I looked at the vocabulary, and then I reframed the procedure of the question, and I now have a roadmap of how to solve the problem, simply because I understand what that definition actually means. So if you ever find yourself going through a Pearson exercise or a problem on the exam, and you read it and you're just like, I don't know what the roadmap is. I don't even know the procedure to begin starting to solve this problem. It's probably because you're forgetting some vocabulary. Return to the vocabulary. Anchor yourself in the vocabulary, because that definitional qualification is going to provide a roadmap for what to target in a problem. Does that make sense? So, let me see how I can articulate that a little bit better. If you're stuck, learn the vocabulary. Then re-express the problem in light of that vocabulary. You will have a much easier problem to solve. Does that make sense? Okay. So, this is equivalently asking me the question, if I have this matrix equation, x1, 0, 1, 5, 1, 2, 8, 4, minus 1, 0, whoopsie, I just put all of them in place. 0, 1, 5, x2, 1, 2, 8, x3, 4 minus 1, 0, equal to, how many entries will my 0 vector have? 3. Okay, so we're going to see, can I get other solutions here? And so let's look at the augmented matrix. 0, 1, 5, 1, 2, 8, 4 minus 1, 0. And what am I setting this equal to? And we call, so what's the vocabulary term for setting your matrix equation equal to 0? Right, so good. This is an augmented matrix of what type of equation? A homogeneous equation. Alrighty, so I like this example for the reason that the first step is a little different than usual. If I go to the topmost, leftmost entry, I land on a 0. Okay. Am I allowed to have a pivot be 0?
No.
No. So I probably want to swap that row out with something else. So there's our convenient one. That could make arithmetic pretty easy. So we're going to make row 1, before we do anything, before we anchor down any pivots, let's swap rows 1 and 2 so that topmost, leftmost entry is no longer 0. Okay, so does the motivation for why I'm doing specifically row 1 and row 2 make sense? Okay, so row 1 and row 2, we're going to do a little tango here. So we got 1, 2, minus 1, 0 now there. 0, 1, 4, 0, and then 5, 8, 0, 0, unaffected on the bottom. Okay, now we're talking, right? So I can go topmost, leftmost. Is that a valid pivot spot? Bingo. So now that I've identified that, what am I eliminating? I'm eliminating everything underneath it. So I'm going to take 5 times R1, since I'm trying to get rid of 5, minus R3, and that's going to replace R3. Top row is unaffected, 1, 2, minus 1, 0. Second row, unaffected, 0, 1, 4, 0. 5 minus 5 is 0. 10 minus 8. Minus 5, and then minus 0. And then zeros, of course. Alrighty. So then in the second row, what becomes the next pivot? Yes, this one right here. I can't take that one because that was cleared to 0. And so now we're using this one. Now I need to get rid of everything underneath it, clear under it. So I'm getting rid of that 2.
We're using a 7 as a pivot.
Oh yeah, I need to write down what we're going to do. Let's take 2 times R2 and subtract it from R3, and then use that to replace R3. So top row is unaffected, 1, 2, minus 1, 0. Second row is unaffected, 0, 1, 4, 0. Bottom row is affected. I get 2 times 0 minus 0. I get 2 times 1 is 2, subtract 2 from that is 0. 4, double that, I get 8. 8 minus a negative is addition, so I'm adding 5 and 8 together to get 13, and then 0. Okay, cool. So is this row reduced echelon form yet? No. But what was the original question? Was the original question to solve this linear system completely? What was the original question? So linearly independent. Can we determine that information from just having it like this? Yes. What conclusion do we reach? It is. Why? Yeah, there's no free variables. There's no room for us to just get to choose something random, right? Either way, I'm stuck with my x3 variable being 0, right? So that's forced. That's going to force this to be 0, meaning that something has to just equal 0, which means it's 0 again. That's going to force both of these to be 0. All of them are 0. No other combination. So this shows me, I don't even have to solve through. I can see that x is going to be 0, 0, 0. Gee, it sure looks a lot like the trivial solution. Is it possible to get anything else other than this trivial solution? No. So flip back in your notes to where you wrote down the definition for linear independence. Does this satisfy that definition? Good. Okay. So now I'm gonna, that's a lot of work to do sometimes this row reduction stuff. So I'm gonna show you some shortcuts. And these shortcuts, I know for certain are on the exam, okay? Or if you don't know the shortcut, then you might just lose a letter grade, you know?
It's alright. Not a big deal.
It's just a letter grade. There are worse things that could happen to you.
It's just
That's untrue.
it's just a letter.
You know, you could get audited by the IRS. That would significantly worse.
The IRS cannot get you in
Both
jail.
your legs were
The IRS cannot put you in jail.
Okay. So I'm gonna show you this. This is one of my favorite tricks. We're gonna determine if the vectors are linearly independent.
Can we make an abbreviation for literally independent?
You can if you want to, LININD, something like that. So long as you can read your own notes, that is perfectly fine. So let's test this out. Let's do V1 is equal to 3,1, and V2 is equal to 6,2. Okay? Now, I'm not going to go through an entire matrix and everything and find the solution set and all that. Here's a really, really fast way to tell. If you can express, if you can basically find a scalar multiple that scales one of them in terms of the other, they're depending on each other. It's a much more intuitive way to think about this. So when my brain thinks, okay, well, the vector V2, in reality, it's basically just I take 2 times what V1 is and just scale it up by 2. In other words, sure looks like they're depending on each other. Yeah? And if you really wanted to go further into the definition, get everything on the same side, and now you're looking at 2V1 minus V2 is equal to 0 vector, which is in itself, what do we call those things? Homogeneous equation. And because we know that we can choose more values of V1 and V2 that are not necessarily trivial, that's in itself a dependence relation. Okay, so this tells me, without having to do any of this, that they're linearly dependent. So keep that in mind. If you can find some sort of constant, if you know that they're scales of each other or something like that, question's over. You already know the answer. They're depending on each other by some scalar multiple. Okay, what about V1 equal to 3, 2, and V2 being equal to 6, 2? Okay? So we don't have to worry about any of the long, complicated process. We just simply look with our eyes. Is that even possible to get some sort of scalar so that they're dependent on each other? No. Impossible, right? So there does not exist some sort of a constant such that I can write one of my vectors as a constant multiple of the other one like I did over here. And if that's the case, well then we're done. What do we conclude?
Linearly independent?
Yeah, they're independent of each other. Okay. Now, that's just algebraic. That's just by looking at it. There's a really, really fun visual way to think about this. I don't know how many of you watched the recording that I made that talked a little bit more on span. What? Let's look at the first scenario where we had V1 is 3,1, so 3,1. This was 3,1. And then the second vector is 6,2, so it's twice as long as that. Well, if I now take all possible linear combinations of these two, we notice they're on the same exact line, right? If anything along this line is going to be some sort of scalar multiple, so all vectors along this are going to be dependent to each other. In other words, if I have two vectors that are in each other's span, in other words, if I can obtain this vector because it's in the span of another vector, that's another way to conclude logically that they are linearly dependent. They are depending on each other algebraically as a constant multiple, they're depending on each other geometrically, as being parallel and contained and constrained on the same span. Does that make sense? Okay. Let's look at the second scenario, where I had 3, 2, and then I had 6, 2. Much different visual picture going on here, okay? These are no longer in the same span. The span of the first vector is going off like this, and the span of the second vector is going on like this, and combined their span, you can access all of R2. And so, graphically dependent, because they're on the same span, graphically independent of each other. They're not on each other's span. So there's a lot of different concepts from the entire first chapter all kind of merging now with this definition, this independence language. Okay, so does the shortcut make sense? Pretty easy. You could probably do this. Does the graphical intuition make sense as well that accompanies the easy start? What time is it?
58, yeah.
Wait, 2:58?
158.
Okay.
It's like I was way over.
Alrighty. Alright. A few quick things. These are mostly intuitive visually. So the set of vectors, let's have P of them, so V1 through VP, is linearly dependent now, if and only if at least one of the vectors is a linear combination of the others. This is just expanding precisely what this trick is in English, because what did we find here? This set of vectors v1, v2, well, they were dependent. Why? Because at least one of the vectors, in this case we looked at v2, was in fact some linear combination of the other vectors in the set, okay? So that is just an English restatement of what we've already looked at. And then it really says, if you're comparing more than just two vectors, it's still okay. Suppose I expanded like my set of vectors to include this 3, 2. So I have 3, 1, 6, 2, and 3, 2. They're still going to be considered linearly dependent. Why? Because even though this really has no bearance on anything, and this is in fact independent of them, doesn't matter. This relation still holds, and I can just scale this vector down to 0. So if I tune this down to 0 volume, and then let this dependence relation stand, it still counts. And so it doesn't matter how many vectors you have, this is just an expansion of that idea. Fun fact, the expansion of this idea is in fact, I think, the leading question of the first exam. Okay, if I have vectors v1 through vp, and let's give all these n entries so we have something to work with, so they have n entries. Then the set of vectors, so now I'm referencing the set as an object, is linearly dependent if p is greater than n. What does that really mean? That's saying if the number of vectors in my collection exceeds the number of entries that are actually in each vector, you're automatically going to have them be linearly dependent. Now, if you only look at this, that might not be the most obvious thing in the world. So here's an example of what this is generalizing. It's generalizing this pattern. Or say it had something like 1, 0, 0, 0. I don't want to make it too big. And then I'm going to put an asterisk everywhere where it really has no bearance what that value could be. Okay, an asterisk 1, 0, 0, star, star, 1, 0, star, 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 1, star, 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 star. Okay, I could have kept going, but I'll just do this. Okay, the dimensions of this matrix are
4, 5, 6.
6. Okay, so then let's ask 2 questions and answer 2 questions. What is n? Okay, the vectors have how many entries? What is p? How many vectors, column vectors, do I have now in my set? Yeah, so then p is equal to 6. So if we're only going by theory, we would say, well, 6 is in fact greater than 4, and so this, without even knowing what these values are going to be, is they're linearly dependent to each other. But further, on the intuitive sense, by having more vectors than you actually have entries, what are we forcing the existence of? Free variables. Okay, free variables are definitionally free. They are free to roam and range and do whatever. Sure sounds like not restricting to only one solution. Yeah? The moment you introduce freedom to that, boom, all trivial stuff is gone, right? You're not going to have only the trivial solution. And that is the key pin that tells you whether something is independent or not. So the moment you introduce the logical necessity of free variables, then yeah, you're not going to end up with only a trivial solution. So we can cut to the chase and automatically know they're going to be dependent on each other. Okay? Does that make sense? So if I had an 11 by 17 matrix, I don't even need to tell you anything else. Are these vectors going to be independent of each other or dependent on each other? Why do I know that they're dependent on each other? Yeah, 17 is way bigger than 11. How many free variables are going to be roaming around?
6.
Yeah, there are going to be 6. Possibly more, especially if we get some cancellation going on, okay? So we'll have at least 6 variables roaming around. That's going to spit out an infinite number of solutions. We're not dependent anymore, okay? So that's all this theorem is really stating. It's this visual intuition. So anchor yourself to this, because then you'll find yourself maybe, I don't know, on an important question that has bearance on your grade, something that will have more columns than it will have rows, and if you need to know its independence or dependence, that's for free. Make sense? Okay, so the very last thing to state is basically that if you have 0 in a list of vectors, no matter what that list is, so long as there is the 0 vector in there, it's going to be linearly dependent. Now, why is that the case? Well, it's because if I introduce, say I have a set of vectors, v1, v2, and the 0 vector, okay, well, by definition, basically, what I've done is I've said, is it possible for me to express all of these to get equal to the 0 vector without all of my weights being 0? Well, fun fact, you can tune the 0 vector up to 1,000,000. So you could have a constant weight of whatever size you want on the 0 vector. It's not going to spit out a trivial solution because that one particular weight in that vector solution is non-zero. That being said, does that have any variance? I can just tune this down to 0, tune this down to 0, and let this range to whatever I want. Okay? The net result is it's still just the 0 vector. But that's more than just a trivial solution. So if you ever have an exercise that gives you the 0 vector in a list, no matter how long that list of vectors is, guaranteed, it's going to be dependent because you will always find a trivial dependence relation by scaling your 0 to something and then dropping everything else to 0. Okay. How do we feel about this? Good? Not good? I need to read the book. I need to do some problems. Okay. So what sections of the textbook are due on Sunday night? everything through 1.7, okay?
When you say do, you want us to write reports or just read it?
As in, I'm going to have a sheet of paper that goes around and you're going to sign on honor that you read it, and that's homework,
Fair.
okay? Because this stuff matters. You cannot be going into 300, 400 level math courses thinking that you can treat it like a Calculus 1 Pearson knockout, okay? Learn the math. Enjoy the math. When you read the text, you're actually going to find a lot more applications than skimming through Pearson. Okay, I will see you on Monday.